welcome to the 13th video in the mathsonlinetuition.com videos. We're starting with chapter 7, and every so often I will take a extra few minutes to go through a particular chapter for the simple reason that I think it's a very pivotal chapter and it's very important. I think in the past I might have alluded to such a thing with the quadratic equation, and now I must emphasize heavily on chapter 7, differentiation. Differentiation is something that you're introduced to very early on in the mathematical A-level world because of its sheer importance in the academic and the career world. Differentiation is one of those areas of mathematics that once you study, you never look back. You only progress and go through and carry on towards bigger and better things. You have double differentiation, triple differentiation, and you just keep going. And differentiation is used for everything, whether it's trigonometry, whether it's numerical values. So many different things encompass differentiation, and it's used in so many different branches of academia, whether it's mathematics, whether it's science as a whole, whether it's engineering, whether it's economics. It's so vast in its principles and its applications, and so I have to stress how important it is for you to really master differentiation, and also its sister, integration. Okay, these two are so vital for your mathematical career that if you do not grasp these concepts, but now specifically talking about differentiation, then really and truly mathematics is not for you. And that's how serious differentiation is as a player within mathematics. So let's get straight into it, and I must emphasize again that you pay very close attention to everything we're about to discuss, and you comb through this video or this chapter if you have it at home as a physical copy once, twice, and many times. So after completing this chapter, you should be able to estimate the gradient of a curve, calculate the gradient focus, a function, calculate the gradient of a curve at any point, find the equation of tangent and normal to a curve at a specified point, calculate the second differential, d2y over dx squared. Did you know differential calculus is an important part of A-level mathematics, as we've already mentioned before? Differentiation enables us to find the exact value where the volume of the box described in chapter 4 is maximized. Okay? Successful business maximize profits and minimize costs. A simple example to explain this might be a drinks manufacturer using cans that hold 330 milliliters, which is your conventional drinks can capacity. If the surface area of the can is as small as possible, then profits are maximized as the amount of aluminium used is minimized. You can calculate an estimate of the gradient of a tangent. In section 5.1, you found the gradient of a straight line by calculation and by inspection of its equation. The gradient of a curve changes as you move along it, and so the gradient of a curve at a specific point is defined as being the same as the gradient of the tangent to the curve at that point. The tangent is a straight line which touches but does not cut the curve. You cannot calculate the gradient of the tangent directly, as you know only one point on the tangent and you require 2 points to calculate the gradient of a line. So very simple stuff. This is a tangent to the curve. It touches the curve at one point, okay, and that is B. Now here is going to show us an example 1. The points shown on the curve with the equation y equals x squared, so that's on the positive side of the x axis, are as follows. Calculate the gradients of 0b, AB, BC and BD. So it's asking for AB, BC and BD. Now again, this is very simple. Remember, all we need to do is employ the formula that we had beforehand, and we need to put in the coordinates. Very simple, very straightforward. What do you deduce about the gradient of the tangent at the point B? So here is the tangent, here is the curve. Remember at point B it touches. So we ask ourselves, so the gradient of the chord, if we scroll down, the gradient of the tangent at the point B is between 1.5 and 2.5. Okay, very simple, very straightforward, not difficult at all. Now you can now zoom in on the section of the curve near the point B. This section shown below is almost a straight line and is close in gradient to the tangent at point B. For the same curve as example 1, find the gradient of the chord BP when P has coordinates. So again, you're just taking these points here, the gradient of the chord joining 1, 1, and you use them as 2 points, and you go through the same procedure. By you have the fact that you have 1, 1 and you have here, then you carry out this process, okay, and you'll get this answer. Very simple, very straightforward. Here are some exercises for you to do. What can you find for the formula for the gradient of the function fx equals x2 and the other function of the form fx equals xn? Examples 2 and 4 show you how to derive the formula and will not be tested. In the following sketch, the gradient of the tangent y equals fx at the point B is found by starting with the gradient of the chord BC. The gradient of the tangent at any particular point is the rate of change of y with respect to x. Please remember the phrasing and the wording used in this particular sentence. The gradient of the tangent at any particular point is the rate of change of y with respect to x. And you're going to come later on to find out why you need to recall the phrasing of that particular sentence. The point B is the point with the coordinates x, x2, and the point C is the point near to B with coordinates x plus h and x plus h squared. Again, look, all they've done is they have these 2 points, they plug them into the formula, and you get the answer. Very simple, very straightforward, no problems there. The gradient formula for y equals fx is given by the equation gradient equals f dash x, where fx is called the derived function. Essentially, the function differentiated once over. Okay, fx is defined as the gradient. So when you differentiate something, you find its gradient. Okay, very simple, very straightforward. Please do read the rest of that. As h becomes small and the gradient of the chord becomes close to the gradient of the tangent, the definition of fx is given as follows. This is not something you need to worry too much about, limits. This is something that you actually learn more about when you get to university and you study mathematics or any numerical degree at university, but they're just trying to get you accustomed to these terms here. Essentially what it means is the following. H is what you can call a particular movement in the coordinate space. So as x plus h, as you have x plus h, so you move by h units, okay, you take it away by the original fx and you divide it by h. So that's essentially trying to convey that the limit of h as it goes to 0, if I'm not mistaken, I believe this is 0, okay, is another way of describing or articulating differentiation. Okay, very simple way of putting a very complicated principle, which, like I said, you shouldn't worry too much about. You can see here the question says fx, or differentiation, okay, when fx equals x3. So here they've essentially taken what we had beforehand except in the denominator we had h, but here they've added x, but you see they've taken away the x as well, so they've made sure that this is identical to the original formula that we had, and they've substituted the x3 in for the fx, carried out again just the expansion as normal, nothing different, and then they've taken away the x and they've left with h on the denominator. On top they've simplified, and then again factorize the numerator, cancel the h's, which gives you 1. So now the denominator is just 1, so we can write it like this. Now as h goes to 0, what happens? This goes to 0, this goes to 0, you're left with 3x2, which means that f dash x is 3x squared. That's essentially all it's saying. We could have just differentiated it using the conventional method that you would have probably learned before or taught very quickly before, which is that the power is to be multiplied by the coefficient, which is here equal to 1, and then subtracted by 1. This is the more rigorous explanation, the technically correct method of achieving that answer. But obviously if you're in an exam and they don't ask you to differentiate using this particular formula, well, if you're struggling for time or you're trying to reserve your time and all you're doing is a simple differentiation equation, well then you'd have 3x to the power of 2 as opposed to doing all of this. But if you are asked to do this particular method, it's not testing your ability of differentiation. That's too simple. It's testing your ability of appreciating where and how differentiation comes from and what it entails. So this is a very important point for you to know. Find from the definition of the derived function an expression for fx when fx equals this. Again, same thing, just have a fraction, carry it out through this particular example, it explains it. Now, we have found that x squared gives the following, x3 gives this, x minus 1 gives this here. Okay? Also, you know that the gradient of the straight line y equals x is equal to 1, and the gradient of the straight line y equals 1 is 0. So you have another two examples. In general, it can be shown that if fx equals xn, where n is the element of the real numbers, then f dash x equals nx to the power of n minus 1. Okay, so the original power multiplies the expression and the power of x is reduced by 1. Again, a very simple way of appreciating this and something that you should remember. Here are some examples. So let's just go through this very quickly. Okay, we have that fx equals xn, f dash x equals, so if we have a x6, b x half, c x to the power of 2, what does that mean? Well, it means that we're going to have a equals n, so n here is 6, x n minus 1 is 5. For b, n is equal to half, so we're going to have half x. What's half minus 1? Well, it's going to be minus a half. C, x minus 2 here is n, minus 2, x n minus 1 is minus 3. Very simple, very straightforward, nothing challenging here, okay? More exercises for you to do. X multiplied by x squared. Again, x to the power of 3, just differentiate it. You can find the gradient formula for a function such as fx equals 4x squared minus 8x plus 3, and other functions of the form fx equals ax squared plus bx plus c, where a, b, and c are constants. Okay, so what does that mean? You can use an alternative notation when finding the gradient function. Again, you find the gradient of the tangent at a point B by starting with the gradient of a chord BC. This time the point B is a point with the coordinates AB, xy, here's the point B, and the point C is the point near to B with the coordinates x plus sigma x, y plus sigma y, delta. It's called delta x and is a single symbol which stands for a small change in the value of x. This is denoted by h in section 7.2. Remember we said that small change denoted by some sort of shift in a particular number of units. Well, it was h before and now they're using this notation. Again, delta here is just a representation of what they are trying to emphasize. And this is very important for people to realize. This is a variable. This is another variable. They are notations being used to emphasize and represent a particular idea or a particular concept or a particular value, numerical or otherwise. Okay? The gradient of the chord BC is, so remember, this comes as y2, this is y1, this comes as x2, this is x1. And here we go. Here you have the gradient. And if you read through this, you'll appreciate that this is called the rate of change of y with respect to x at the point B and is denoted by dy dx. Okay, so the limit of the rate of change of y with respect to x as the delta x goes to 0 is called dy dx, or the differentiation. Dy dx is called the derivative of y with respect to x, also noted or denoted as f dash x. The process of finding dy dx when y is given is called differentiation. When y equals xn, dy over dx equals nxn plus 1. Remember this one here? Same thing. You can also differentiate the general quadratic equation, which is here, using that definition. Okay? So you can see that they've differentiated it. Very simple, very straightforward. They've taken that shift, that small shift in delta here, and they've taken it away from the original y, and again at the bottom they just have x plus what they had in the denominator minus x. Okay, these two cancel out to give you this one here. And now essentially they've said as sigma x goes to 0, so this goes to 0, this goes to 0, and essentially well, if we factorize this, okay, we can see that everything will be going to 0 except that we have 2ax plus b. Okay, and this is essentially what we would have had should we have used this particular formula quickly, a shortcut to find the differentiation of this particular equation. So very simple here, you can see what it's trying to express. Consider the three sketches below. Now find, or you can see their gradient. Differentiated, x is gone, differentiated because the constant is equal to 0. And then in example 6 and example 7, you have the ability to go through some of these questions, find the gradient of y equals fx at the point half 0. So differentiated it first, okay, then essentially all they've said is, right, if we have 1/2 equals to x, what are we going to get? We're going to get -4. That's as simple as it is. So they differentiated it, and then they've substituted the coordinate. Find the coordinates of the point on the graph of y equals fx with the gradient, where the gradient is equal to 8. So we know the gradient is equal to 8, they've differentiated it, so we have x equals 2, we have the x coordinate. Put it back into our equation here, we get y is 3, so we have 2, 3. So at 2, 3, that coordinate, okay, xy, we have that the gradient is 8. And for c, okay, find the gradient of y equals fx at the point where the curve meets the line, y equals 4x minus 5. Again, you can see that they've carried out the quadratic equation procedure, and then essentially all they've ended up with here is telling that x equals 1 or 2, and so we have this particular result. And this is an exercise for you to perfect this. Okay, I'm going to stop there, and we'll carry on with our second video with chapter 7, because I think it should be split up into 2 parts. Till then, thank you very much for listening, and take care. Bye bye.